Hi folks, so I'm pleased to be here talking about a subject I like, which is about capturing. So who knows about capturing? Nobody? Come on guys, nobody knows about capturing. Right, I didn't even say what capturing was. So it's not capturing someone, with a net, as you can see in movies. It's about capturing packets. So it's about how capture is performed with lead pickup, for example, how we can be faster, how we can use GPU for that, and how we can also see things happening in logs, and how we can play with syslog, whatever logs you have, and how we can inject traffic in logs, and everything we can do to disturb your intrusion detection systems. So I'm Sebastien Tricaud. I run a company called Pigviz Labs. We do data mining, and I'm also the Chief Technical Officer of the HoneyNet project. So we'll first see a short introduction of what I'm going to talk about. We will have a look on how the network capture is performed. Then we'll go for a log capture, have a look at CUDA, and do some visualization. So the context is, once upon a time, someone called Mr. Neil Ziering said, the attack data is often lost in the noise of events. So who knows Neil Ziering? Guys, come on, it's very famous. All right. He's actually the CTO of the Information Insurance Directorate of the NSA. So he's the guy actually giving the advice for the various agencies of the United States on some, some trends and what's happening. So when someone like that said the quote I just showed before, he knows what he's talking about. So this talk is mostly all about how capture can be performed and managed effectively to find incidents on large networks. So what I call incidents is either attacks or some people are trying to do data leaks and things like that. So when we want to find incidents, the best way is actually to just sniff the traffic. Because whatever the IDS you're going to use, if you just keep sniffing, you will have everything, including the documents that are being leaked, because you sniffed everything. When you sniff everything, it means that you have to store everything. It's another issue. But still, some companies do that. So once you've captured the traffic, there's someone who will report to you an incident. Because you don't know you have an incident until someone goes up to you and tells you, oh, there's something that happened last week, or blah, blah, blah. So someone reports an incident, and then you know about the time when that happened. And because of this, you can investigate. If you don't have this information, you are not going to see your traffic all the time, all day long, all night long, unless you are someone I don't want to shake hands. And usually what people do upon this traffic, they run software like Snort, simply to classify a little bit what's happening. Because Snort has root sets. It has more than 5,000 root sets. So are you going to have a brain that can remember all those 5,000 stuff? No, you're going to use a tool that has that. So whatever the tool actually, but it's the idea of running something that has a knowledge database of incidents that you run upon your large traffic. So I'll give you just two countries examples that are facing this issue. There is a country of 20 million people that is that needs to handle 30 gigabytes of net flow traffic per 24 hours. And it's not a staff of 5 million people working on those captures. It's a staff of 10 people. So you have 10 people who need to handle such a large amount of events. So we are talking here about large stuff. Another example of 45 million people country, I can't give names, but if you look on Wikipedia, maybe you'll find it. They have 3 million of net flow per 5 minutes of capture. So they have quite a lot of, again, network net flow that is mandatory for them to investigate and to perform the investigation. So again, they have to store this, and when it's stored, they have to go and dig in it and try to extract information. So let's see how network capture is actually performed. So I guess a lot of you know this code, which is basically using libpk for packet capturing. So you basically run a loop upon every packet. You get the time, and then you can do everything you want with the IP packet you decoded. So how does libpk works? So it works at layer 2. I don't know if some people among you have already been setting up a firewall and then trying to sniff whether the packet was blocked or not. It wasn't blocked because it was layer 2 and your firewall is layer 3. And the thing is with libpk is that the packet is copied, right? So when the processor is actually busy, the packet is not copied because it's not a mandatory operation. It means that there is a packet that goes straight to the layer, the network layer, without being copied, without letting you the ability to sniff your traffic, simply because it's not efficient. There were some zero-copy patches. Bro IDS is actually using a custom libpk just for this, just to avoid the copy, but it's a modified version. Another way to do packet capturing is to use a netfilter, which has some queue mechanism. So netfilter has 3 mechanisms actually, which is the connection tracking. The queue means that you get a packet in the netfilter queue that will then be sent to the libnetlink, which is the user space library. And after it goes to the libnetfilter queue library, that is used for anything like IDS that will want to get packets and then block a specific packet according to a given rule set. There was a project called Snort Inline that was actually implementing the feature of having Snort sniffing not with libpk but with netfilter. And netfilter is more reliable because you already work with the network layer. Unfortunately, you don't have a Berkeley packet filter system, which is provided with libpk, but there are some ways you could use that anyway. Another way to resolve this issue of this multi-packet capturing possibilities you have is to use the DAC library, which is written by the SourceFire guys. And today, Snort relies on the DAC library. So if you want to run and compile Snort, you need to run and compile the DAC library first. And the DAC is the data acquisition library. It works with several types of capture. And I guess in the future, if we have more, it's just a plugin that you add to this library, and then Snort doesn't need to change any line of code. The other ways to capture would be to use daemon logger, but daemon logger relies on libpk, which has all the mistakes of libpk. You have streams. So streams is a great new tool. I'm sure most of you don't know about. I have the URL on the very at the bottom of my slides. You can get the source code. It's a project supported by the Honeynet project where you can deal with your pickup in a NetFlow manner and investigate with command lines. So it's way easier and it's sharper than Wireshark because Wireshark may be very slow if you have large pickups, and that works fairly well. Another way to do packet capturing is to use the work done by Luca Derry, who is the author of NTOP. He did some work on a PF ring. That it's a more efficient way of capturing. He played with quite some tricks with mmap, memory mapping. And another way is to use a GPGPU. Then, perhaps you got your packet. You're not sure about it because it was copied, right? So let's say that the packet arrived, and the thing is that when the packet arrives to your application, is that it can be fragmented. If you run signature matching, it may be encoded in UTF-8, 16, whatever. If you have a protocol like RPC, it needs to be decoded. And actually, the attack can be located in a different model, different layer. If you have a layer 1 attack on your network card, say in your firmware, then there is nothing you can do about it because it's at the lower layer, right? So let's have a quick look at how fragmentation works on the Linux. First of all, you have two different files that have two different naming conventions, and there are some common functions that are actually overwritten in the different files. So I guess it's a mistake. They don't do the work because it works the way it is, and it's very sensitive, this part. It may introduce some evil bugs, so it works. People don't touch it. It's like, it's a sin to touch on these files. But anyway, if we look closer on how it is performed on IPv4, we do see that there is inside a function called iptfrag that the defragmentation is performed. And this defragmentation is only called by two functions. The first one is IP local deliver, in case you want to deliver a packet to a local interface, or IP called RHN. And that function is only called if you have an interface that is tied to the machine. It means that if you do forwarding, it won't defragment. Actually, but you have to know the trick. If you play with netfilter, only if you do a mod prod and fcontract IPv4, there will be a stateful machine loaded in the kernel, and that will do actually the defragmentation. But there is something you have to know. So now that we capture things, we want to find evils in it. And Snort, if we take this example again, has some signatures that can either match on content, which is basically a binary form, or just find a pattern, like here, it's a very nice sentence. Or you can also do some pattern matching. So if you do some pattern matching, the question is, do you think Snort does pattern matching on every packet? Who thinks so? You have patterns, in all the signatures. Go ahead. Who don't think so? Hey, raise your hand. Nobody thinks so. Don't think so. Who's not sure? All right. Of course, Snort does not do pattern matching on every packet. Think of the overhead. Pattern matching is fairly complex, and you can do that on a packet basis. So we assume that it's within the Snort engine that long patterns are easier to find. And how Snort does pattern matching? First of all, Snort tries to find the longest pattern within the signatures with the packet. And if it finds it, then it goes to a pre-qualification phase. And after, in the end, you have a PCRE that is being tried on the machine. So usually, I don't know if you noticed, but in the Snort signatures, when you have a regex matching for a packet, you don't have just a regex matching, you have something else. Because you need to have that for the pre-qualification. If you don't use that, if you just do pattern matching, then you're introducing overhead in the engine. Another thing is about NetFlow. It's not about Snort. Again, about how we can deal with such events. It's easier to investigate with a network flow. As you've seen, the numbers I showed earlier is actually for 2 countries, right? And only for NetFlow. If we don't do NetFlow, it's way more, and it's really, really hard to manage. And it's easier to understand a machine that communicated with another just by looking at the SYN packet of the TCP or the first connection of the UDP stream. So again, the application streams was designed to help you in this area. Now let's have a look at log captures. Log captures. So one thing is that logs are highly used by investigations, because whenever there is something happening, you need to have the Apache logs to investigate on who went to the website and things like that. So logs, the staff relies heavily on logs. So who cares about logs, actually? Who cares about the log's weaknesses? Who cares about log normalization?